Hello everyone, welcome to this tutorial. My name is Amir Ahari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to calculate growing season lengths in the Google Earth Engine platform using Python API programming and XEE library. This tutorial is very beneficial for agricultural studies and allows you to understand about the period of time in which you can do cultivation or farmers can do cultivations growing degree days during the growing season. That is really important criteria. So in this tutorial, at the end of this tutorial, you will be able to plot the annual variations of growing season lengths. As you know, each year we have almost 365 days, and it is important to know how many of these days suitable for agricultural activities. And if any change or any variations actually happened in the growing season lengths, actually you can highlight it using this index. So now in this tutorial you will be able to make such kind of plots for your own region of interest, and that should be very interesting tutorial for all of you who are interested in the agricultural studies. So make a new notebook. Let's do it together in the Colab environment. In the first step, we need to make a new notebook in the Colab. I skipped this part because all of you may know how to make a new notebook in the Colab environment, and then start with calling necessary libraries before further processing. So in the first step, I'm gonna call those of libraries essential for connection between Earth Engine and Colab environment. The first is XEE and the next one is GEE map. Then I want to call X-array structure because we want to convert our Earth Engine data to a multidimensional format. So import X-array as XR. So run the first cell and you can see the Colab server is connecting. Once the connection is made, then the libraries start loading. In another cell, you can actually install XEE library because the XEE library not built-in available in the Colab environment, and we need to install it separately. Hopefully in the Colab environment, it is really easy to install some other libraries that is not available here. For example, just start with pip install, for example, XEE, and then import it as a XEE library. So let's run this cell again. You can see very easy actually the process of installation is done, and once you see the successfully installed, meaning that everything is fine, you can go for the next level. So in the next step, I'm gonna actually make a connection between Earth Engine and Colab. Until this, we were actually just calling necessary libraries for processing. Earth Engine.authenticate. First start with authentication and then initialize your Earth Engine ID, project ID. What is the project ID? If you go to the code editor environment here, upper right, you can see your account information. Just go to the project info and find your cloud project ID, copy and paste it, just like this. And Cloud project ID is unique and also very confidential, is unique for each user. For example, for me is Earth EE dash Amir Hossein Ahari, but for you and others could be must be different. Definitely depends on your ID address. So the next one is OPT URL. The OPT URL is a kind of address that mentioned in the XEE library instruction. If you search on the net about Google Earth Engine and XEE, you will find a GitHub link in there, all instructions available how to deal with XEE libraries in different scenarios. The OPT URL copy and paste like this. And now Colab asking us permission to make a connection with Earth Engine. Connection is granted by clicking on allow and clicking on account information. Go to continue and continue again. So you can see sounds there is no problem and everything is right. After 27 seconds, the connection is made. In the next cell, I'm gonna select the study area. So hopefully we can make an interface for a study area and find it on Google Maps satellite easily without any challenge. So now make a new variable as map from GEE map library, call map function with a kind of base map. For example, the satellite is my interested base map. And then call the map variable. After a few moments, you will have an interface allows you to select your region of interest without any challenge. In this tutorial, I'm gonna select a large area in the European countries or the European countries to see how growing season changes from upper latitudes to the lower latitudes. Through the rectangle tools, it is very easy to select your region of interest like this, or you can edit it by clear and draw it again. For example, there it is. You can actually see growing season variation over the region selected. In the next step, we want to have this rectangle as a new variable. So ROI equals to, from the map, select the last feature. There it is. It's very easy. Feature dot geometry. We want to have it as a geometry layer. Let's run it and go to the next line here. If you make a print from ROI, you can see a polygon with 5 vertices is available. So sounds ROI is fine. In the next step, we want to call the satellite data. Actually, in this tutorial, we want to actually show you how to calculate growing season lengths through the xclimb library. The input for the growing season lengths is the average daily temperature data. So you can find any average daily temperature in the Google Earth Engine platform and bring it into Colab and do this process. So let's go to the code editor, through the search places and dataset. Directly you have access to vast amount of data available in the Earth Engine data catalog. I prefer to use one of the most famous data catalog in the Earth Engine, including temperature and other climatological variables. This is ERA 5 data. ERA 5 for land is available with daily frequency and monthly, but remember to use the daily data. It is very important to actually call the daily data for this tutorial because the growing season lengths need the daily variation. The daily length selected here, go to the data properties here, click on copy the collection snippet and then paste it into the code. Collection equals to aggregated daily product. Then make a filter date and filter your data to a period of time, as we want to compare the growing season lengths for each year separately, each year together, it is important to actually select a period of time at least greater than 2 years. For example, I'm gonna start from 2000 to 2020, for example. If you go to the era 5 data availability, you must make sure the data set is available for the period of time. Go to the data characteristic and you can see the availability ranges since 1950s to present. So in the next step, go to the bands and find your target data. The input must be the daily temperature. So the air temperature, a temperature 2 meters selected, and then make a function select, write the select function and call the temperature data. But remember that the input temperature for this tutorial must be degrees Celsius, because if you read the description, you will understand that degree Celsius is the actually key units in this process in the libraries we targeted each client. So that's why we need to do a conversion from the Kelvin to degrees Celsius. If you go to the data description here, you will find that the temperature unit is Kelvin based, and we need to subtract it from 273 to make sure the output is based on the degrees Celsius. So then make a loop structure through the map, click on enter. This helps you to write the codes easily, and also with going beyond the available space in the database in the cell. So here we need make a lambda, an unknown function. The lambda is one of the lambda like this. The lambda is one of the useful resources in the Python, allows us to make a quick function using map. So each input image as a each input data considered as an IMG, and finally we want to subtract the input from 273.15, a constant value for conversion between Kelvin and degrees Celsius. Then we want to have all properties of input data for the output. That's copy properties like this, the input properties, copy to outputs. That's property names. There it is. So let's run the collection, and after a few moments print it out to make sure everything is fine. This is the collection data set. Definitely you will face with an error because more than 5,000 data actually called here. That's why you cannot see the output, but ignore this process printing. I mean, if there was any errors and mistake in the code, definitely you actually face with such kind of errors here. So you don't need to make actually printing for whole of the data, just you can make a print for some of the data through the limits to, for example, 10. The limit is a kind of function allowing us to make a print from a 10 first data here. Just make sure everything is fine and temperature data selected and all properties available. That's all. No need to see all the variables, all the features in the time series data. So the collection is created, but as you can see, the image format is image collection. This is the step. Now we want to calculate the growing season lengths, but the problem is for the Python libraries, the Earth Engine image collection is unknown format. That's why we need a bridge. We need actually a kind of tools or functions that convert the image collection format to the multidimensional format that is acceptable for other resources in Python. Here it is, we have the XEE library. XEE library now allowing us to do this conversion to calculate a growing season lengths. So now a new data set. Now we want to convert the image collection into a data set format, multidimensional structure. So from X array, open the data set just like this. Which data? The collection is the target data. Sets engine to EE, CRS, the coordinate system, EPSG 4326. This is a unique code for WGS84 coordinate system. So the scale could be, for example, 10 or 20 kilometer. If you go to the data properties, you will find the spatial resolution here. The pixel size is 11,000 meter or 11 kilometer, but I prefer, as I selected a larger area, I prefer to resample it to, for example, 27 kilometer, because I've selected a very large area and no all details not necessary, just we want to see whole of the pattern changes in the region. That's why I prefer to resample it to 27 kilometer, allowing me to have a higher speed of processing and facilitate extra analysis here. So, and the scale must be in the degree format because the coordinate system is EPA WGS 84. 1 degree equals to 100 kilometer, 0.27 means 27 kilometers here. So the next is the region of interest or geometry sets to the ROI. Now let's run the cell, and after a few moments you will have another cell and you can see the data set available here. So now we are waiting for this conversion, and also this is the revolutionary things that we can convert the Earth Engine dataset into X-array structure, because from now on we can apply various amount of analysis that that we couldn't do it before. Yeah. So because the Earth engine functions are limited, and as you can see, more than 5,000 variables now printed without any challenge. We have a multi-dimensional data structure. The main variable is temperature, coordinate system. It's very fantastic. So in the next level, in the next step, now we want to focus how to calculate growing season lengths. So in the first step, we need to actually prepare the data. First, you must make sure the data frequency is the daily. That's why we need to check it by a function from X array. Infer frequency tells you the data is daily or not. Infer frequency for the ds.time. One of the dimensions is the time. ds.time means select the time information, and infer frequency, check the frequency of this data. When the D returns, meaning that this is the daily format. So now we know that the Python reads this data as a daily data. So in the next step, we need to add a unit of measurement for this product. And now we have the temperature data with a degree Celsius, but the degree unit doesn't mention here. That's why we need to add it to the existing data set. We have a variable temperature 2 meter, and we want to add a new attribute here to add a new attribute about the unit of measurements. That's why at attrs enters, actually the new attribute here is the units, just like this, equals to the degree Celsius. The format should be like this. Let's run and go to a next level, the ds. Now we have the same data set with a new attribute. The unit is based on degrees Celsius. These actually checks and analysis and preparing is essential to deal with xclimb data sets, so xclimb the library. So the xclimb is a kind of library allowing you to apply various kind of actually climatological indices on satellite data. So it is very, very interested things. And now we are integrating Google Earth Engine, Python, and XEE library through the XEE libraries to facilitate such kind of analysis that we couldn't actually apply it on Earth Engine alone. So the next, we wanna install the xclimb because xclimb not built-in available. So now through the pip install, just install it and then import it. Very easily. So run it and you can see it's installed without any challenge and without any error. So in the next step, we want to actually bring this index, growing season lengths, GSL equals to, so from xclimb dot indices call growing season, this is growing season and this one is growing season lengths. Couple of arguments essential here. One of them is TAS. First, you can read here the growing season start with first sequence of minimum lengths of consecutive days above the threshold and ends with the first sequence of the same minimum lengths of consecutive days under the threshold. That's why the temperature TAS is the first and main parameter. So TAS, air temperature, equals to, from the data set, select the main variable. That was the mean, what was the name of the variable? The variable name was temperature 2 meter. Yes, temperature for 2 meter, just like this. This is the first argument. The next argument is the threshold. Based on which threshold we want to actually find the growing season. Typically, 5 degrees Celsius considered as a threshold, temperature threshold for the growing season. If we have for a 5 temperature degrees Celsius for consecutive days in a row, then meaning that the growing season starts. So the next one is the threshold equals to, based on the example here, make a string and enter 50 the degree Celsius, just like this. And you remember we actually identified the units based on the degree Celsius. The window size refers to the number of the days that a temperature should be above the threshold. For example, if the temperature was greater than 5 degrees Celsius for 6 days in a row, meaning that the growing season starts. So the window means the number of the days in row temperature greater than the threshold. So you can change it based on your, or you can optimize it based on your region of interest. So now there it is, the window equals to, so for example, the 6 here generally, and the mid date. Here you can actually see the descriptions about the functions. For example, the mid date is the date of the year before which the season must start and after which it can end. And typically, we consider July, at least in the north hemisphere, July considered as a mid date, the July 1st. This is the format, months and day. So the next argument is mid date. Mid date, just like this. Mid date equals to, for example, July month 7 first. So the next one is the frequency. We want to see the growing days, actually the growing season lengths with the annual format in the output. That's why the frequency should be yearly resample. And now we want to resample the output. The input is daily, but the output shows the annual map that ranges growing season lengths for each year separately. So the frequency, just like this, equals to number 7. Sorry, it should be ys. And the next one is not necessary. The operator could be greater than, equal, greater than what, greater than 5 degrees Celsius. The default is greater equal, so meaning that if the temperature is greater than or equal 5 degrees Celsius for 6 days in a row, meaning that the growing season starts. These are the parameters or factors we are considering to define the growing season length. As I mentioned earlier, feel free to change it or optimize based on your region of interest or based on some updated information you may find in the papers. Let's run a code. Typically takes at least for 20 hours and 27 kilometer spatial resolution. This process takes a couple of minutes, but less than 5 minutes or 10 minutes for sure. You can find the output. So if you face with any challenge for this tutorial, feel free to pick the code link below this video on my YouTube channel. There is a description box below the video allowing you to actually find extra information about the course, such as the code link and etc. And if you had any problem, you can compare yours with mine. If problem is still exists, please feel free to reach me out on comments in the comments and put your comments there. And I'm asking you to share this tutorial for everyone who is interested to learn about the remote sensing. I will try to share my knowledge actually to empower remote sensing communities, and I want to show you how we can use remote sensing to address the environmental issues and actually the monitor the earth and check how everything is changing. So feel free to share it with others, and because these kind of tools necessary to learn for environmental monitoring and climatological studies. So I will pause the video and resume it again once the process is done. So as you can see, after 4 minutes, process is done. And now make a new cell and check the output bands. So as you can see, we have a multidimensional array. We had 20 years daily data, and now we have 20 annual growing lengths, actually growing season lengths. And here there are indices and also there are attributes. Here you can check the information about the longitude, latitude, and time. You can find this information, and the longitude and also the long name and the description shows the number of the original series in season between a start and end days. So the unit refers to the number of days. There it is. And now make a code and make another cell for the visualization. So the variable name is the GSL, just like this, and the GSL dot plot x equals to longitude, because we have the longitude for the spatial visualization. Y dimension sets to latitude. It is also available here. The next, the call equals to the time, because we want to have a multi-temporal visualization process. So in each row, when you have a multi-temporal layers, multi-temporal visualization, you need to identify how many maps will show in each row. You can define it through the call wrap. For example, I will set 5. I want to have 5 maps in each row, and then to avoid outlier values for the visualization, sets the robust as true. And let's run a plot, and after a few moments you can see the same output I showed you earlier. This is a map that shows the lengths of growing season based on the days. For example, the darker area, shorter growing season, and the brighter area, actually greater growing season, or longer growing season. As you can see, in the high latitude area, growing season length is very short, around between 100 and 200 days. 200 days per year is you can actually do agricultural activities, but in the lower latitude region of in these areas, for example, you can see over 250 or over 300 of 300 days per year. The situation is actually good for agricultural activity, at least from the temperature point of view. If you want to get exports, so from this plot with a high quality, you must import matplotlib.pyplot as plt. There it is. And then get the export using savefig. Couple of arguments. The first, name of output. It is growing season length with PNG format, DPI dot per inch 360. Gives a good quality. And if you want to have all the elements inside a unique map, BB box inches must equal to here tight. Now let's run. After a few moments, you will see the output in the left panel. So now I'm waiting to see if actually you cannot see the gsl.png. Just make a refresh and then download the output easily without any challenge. So find an address to save the output. Now let's see how the output looks like here. There it is. Now we have a very, very high quality map that shows the length of growing season. I hope you like this tutorial, and I'm asking you to try to learn this process, because this is very, very essential for environmental studies and agricultural studies, and feel free to share it with everyone in all around the world. I hope you like it as much as I did. Thank you for your attention.